High above the frozen landscapes of our planet, curtains of light dance across the darkness. Green ribbons twist and fold through the night sky, sometimes joined by violet, crimson, and pale blue. For thousands of years, humans have gazed upward at this celestial ballet, their minds spinning stories to explain the impossible. The Vikings believed these lights were reflections from the shields of warrior maidens riding across the heavens. Indigenous peoples of the Arctic saw the spirits of their ancestors playing games with walrus skulls. In Finnish folklore, the lights were sparks thrown up by a mystical fox sweeping its tail across the snow. Each culture wove its own mythology around this phenomenon, yet none could have imagined the truth that lay hidden in the fabric of space itself. Today, scientists have uncovered something remarkable about the Northern Lights, something that challenges what we thought we understood about this ancient mystery. The discovery wasn't made in some distant observatory or through a telescope pointed at the stars. It emerged from satellites orbiting our planet, from particle detectors measuring invisible forces, from researchers who questioned assumptions that had stood for decades. What they found reveals that the aurora borealis is not simply a beautiful accident of nature, but a window into processes that connect our world to the sun in ways both violent and delicate. The light show playing out above the Arctic is evidence of an ongoing battle between our planet and the star that gives us life, a conflict that has raged for billions of years and continues at this very moment. The forgotten truth about the Northern Lights tells us something profound about our place in the cosmos, about the forces that make life possible, and about the invisible shield that protects everything we know and love. Before we journey into the depths of this mystery, take a moment to settle yourself. Let the weight of your body sink into whatever surface supports you now. Feel the gentle pull of gravity anchoring you to the earth. Your breathing can slow, become deeper, more rhythmic. There's nowhere you need to be, nothing you need to do except listen and drift along with these words. Close your eyes if you haven't already. Let the darkness behind your eyelids become a canvas for the images that will unfold. The Northern Lights are waiting to reveal their secrets, and you're about to understand them in ways that few people ever have. This journey will take you from the surface of the sun to the magnetic heart of our planet, through time and space, through centuries of misunderstanding into clarity. If you're enjoying this exploration, if you find peace in these moments of learning while relaxing, consider subscribing to this channel. We create these journeys for you, these passages between knowledge and sleep, these bridges from curiosity to rest. And if you'd like, leave a comment telling us where in the world you're listening from right now. Are you in a city apartment with traffic humming outside? A quiet house in the countryside? Perhaps you're actually somewhere near the Arctic, where the lights themselves might be dancing above you at this very moment. Wherever you are, you're part of a community of minds that finds comfort in understanding, that discovers relaxation through discovery. Now, let yourself float into the story that's about to unfold, a story written across the sky in light and magnetism, a story that begins 93 million miles away. The sun does not sit quietly in space. Every second, deep within its core, hydrogen atoms collide with such tremendous force that they fuse together, creating helium and releasing energy that will take hundreds of thousands of years to fight its way to the surface. When that energy finally emerges, it does so as light and heat, but also as something far stranger. The sun breathes out a wind made of particles, electrons and protons, stripped from their atoms, racing outward in all directions at speeds that would cross the distance from Earth to the Moon in less than an hour. This solar wind is not constant or gentle. It surges and ebbs, sometimes strengthening into storms that carry billions of tons of matter away from the sun's surface. These storms are born from the sun's magnetic field, which writhes and twists like a living thing, forming loops and arcs that can suddenly snap and release vast quantities of energy. When these magnetic structures break, they hurl plasma into space in events called coronal mass ejections, clouds of charged particles that can be larger than the sun itself. For centuries, humans looked at the sun and saw a perfect circle, a steadfast companion that rose and set with comforting regularity. They had no way of knowing about the violent seething on its surface, the explosive flares, the constantly churning magnetic chaos. Even when Galileo first turned his telescope toward the sun in the early 1600s and discovered sunspots, the true nature of our star remained hidden. Those dark blemishes on the solar surface were cooler regions where strong magnetic fields suppressed the normal convection that brings heat outward. But their significance wouldn't be understood for hundreds of years. The key insight came gradually, pieced together by scientists who noticed patterns. They observed that sunspots came and went in cycles, lasting about 11 years. They noted that during periods of many sunspots, the Earth's magnetic compasses would sometimes go haywire, their needles swinging wildly as if something invisible was interfering with the planet's magnetic field. Telegraph operators in the 1800s reported strange currents flowing through their wires during these magnetic storms, currents strong enough to shock them or even set their equipment on fire. Some operators discovered they could disconnect their batteries and still send messages using only the electric currents induced by the disturbance itself. In September 1859, something unprecedented happened. Astronomers watched as a massive solar flare erupted from a complex sunspot group, so bright it could be seen against the sun's face without magnification. Within 18 hours, the fastest particles from that eruption reached Earth.
The result was the most powerful geomagnetic storm ever recorded. Aurora Borealis appeared as far south as the Caribbean. Telegraph systems across Europe and North America failed. The sky glowed red and green and purple from horizon to horizon, bright enough that people could read newspapers by aurora light at midnight. Miners in the Rocky Mountains woke before dawn, convinced by the light that morning had arrived. Birds began chirping their dawn songs in the middle of the night. The Carrington event, as it came to be known, revealed that the sun and Earth were connected by invisible forces, that events on the surface of our star could have immediate and dramatic effects on our planet. But the mechanism behind this connection remained mysterious for decades more. Scientists knew that the sun emitted light and heat, but the concept of a solar wind made of particles streaming constantly through space wasn't proposed until the 1950s. Even then, many researchers were skeptical. How could particles travel such vast distances through the vacuum of space? What would push them outward from the sun? The answer came from studying the tails of comets, which always point away from the sun regardless of the comet's direction of travel. Something must be flowing outward from the sun with enough force to blow those gossamer tails across millions of miles of space. That something was the solar wind, finally confirmed by Soviet and American spacecraft in the 1960s that directly measured the stream of particles flowing past Earth. The Northern Lights, it turned out, were the visible evidence of a collision between two vast systems, the sun's explosive atmosphere and Earth's protective magnetic bubble. But the details of exactly how solar particles created those dancing lights remained elusive, and it's in those details that scientists have recently discovered something that changes everything we thought we knew. The solar wind is not uniform. It flows in streams, some fast, some slow, creating boundaries where different speed streams collide and create turbulence. Think of it like a river with currents of different speeds creating eddies and whirlpools where they meet. But unlike water, the solar wind carries a magnetic field with it, frozen into the plasma and dragged along as the sun's magnetic field lines are stretched into space by the escaping particles. These magnetic field lines emanating from the sun spiral outward in a pattern shaped by the sun's rotation, creating something called the Parker spiral, after the physicist Eugene Parker, who predicted its existence. As Earth orbits the sun, it moves through different streams of solar wind and different regions of the interplanetary magnetic field. Sometimes our planet encounters fast streams, flowing at 800 kilometers per second. Other times, slow wind barely making 300 kilometers per second washes over us. And occasionally, Earth's orbit intersects with a coronal mass ejection, one of those massive clouds of plasma hurled from the sun during an eruption. These are the events that cause the most spectacular auroras, but scientists recently discovered something unexpected about how even the everyday solar wind contributes to the northern lights. The discovery began with an anomaly that didn't make sense according to existing theories. Satellites monitoring Earth's magnetosphere detected bursts of electrons accelerating to extremely high energies during periods when the solar wind seemed relatively calm. There was no obvious source for the energy needed to accelerate these particles. It was as if electrons were being plucked from the near-Earth environment and flung downward toward the atmosphere with tremendous force. But the mechanism doing the flinging remained invisible to instruments. Researchers at NASA and space agencies around the world began studying these events more carefully. They combined data from multiple satellites positioned at different points around Earth's magnetic field, creating a three-dimensional picture of what was happening in the space environment during auroral displays. What they found was astonishing. The electrons weren't being accelerated by a single simple process as previously thought. Instead, multiple processes were working together, some operating millions of miles from Earth, and others occurring just a few thousand miles above the atmosphere. The solar wind carries energy and particles toward Earth, but our planet doesn't sit defenseless in this stream. Earth has a magnetic field generated deep within its liquid iron core, where churning convection of molten metal creates electric currents that in turn produce magnetism. This field extends far into space, forming a protective bubble called the magnetosphere that shields us from the direct impact of the solar wind. Without this magnetic shield, the solar wind would gradually strip away Earth's atmosphere, leaving our planet as barren as Mars, which lost most of its magnetic field billions of years ago and subsequently lost most of its air and water to space. The magnetosphere is not a perfect sphere. The pressure of the solar wind pushes it in on the sunward side, compressing it to about 10 Earth radii, roughly 60,000 kilometers. On the night side, away from the sun, the magnetosphere is stretched out into a long tail that extends more than 6 million kilometers into space, far beyond the orbit of the moon. This tail is a critical part of the story of the Northern Lights, something scientists didn't fully appreciate until recently. Within the magnetotail, as it's called, magnetic field lines from Earth's north and south poles are stretched out and eventually connect with each other in a process that shouldn't be possible according to simple magnetic theory. When magnetic field lines with opposite directions come close together, something dramatic can occur. They can break and reconnect in new configurations through a process called magnetic reconnection. This might sound abstract, but it's one of the most powerful energy release mechanisms in the universe. When magnetic field lines reconnect, the magnetic energy stored in those stretched and twisted fields is suddenly converted into kinetic energy, the energy of motion. Particles near the reconnection site are accelerated to tremendous speeds in microseconds.
In Earth's magnetotail, reconnection events launch plasma back toward the planet, creating flows of particles and energy that slam into the inner magnetosphere. These injections of energy create disturbances that ripple through Earth's magnetic field like waves on a pond. Scientists have known about magnetic reconnection for decades, but what they discovered recently is that it happens far more frequently than anyone realized, and in far more places throughout the magnetosphere. High-resolution satellite observations revealed that reconnection occurs not just in large dramatic events, but in thousands of small bursts happening constantly throughout the magnetotail. Each tiny reconnection event accelerates a population of electrons. These electrons then surf on electromagnetic waves, gaining more and more energy as they ride toward Earth. The waves themselves are generated by instabilities in the plasma, places where the flow of particles and the magnetic field configuration create conditions ripe for wave growth. The electrons and waves interact in a process called wave-particle interaction, where energy is exchanged back and forth. Some electrons gain energy and accelerate toward Earth. Others lose energy to the waves. But on average, a significant population of electrons emerges from this process with enough energy to penetrate deep into Earth's atmosphere when they finally arrive. This is where the northern lights begin, in this complex dance of reconnection and acceleration playing out across millions of cubic kilometers of space. But the journey from the magnetotail to the visible aurora in Earth's atmosphere involves several more steps, each discovered through painstaking scientific detective work. The accelerated electrons flow earthward along magnetic field lines, guided by the planet's magnetic field toward the polar regions. This happens because magnetic field lines act like highways for charged particles. An electron or proton moving through space will spiral around a magnetic field line, trapped and guided along its length. Earth's magnetic field lines emerge from the south magnetic pole, arc through space, and descend back into the north magnetic pole. Particles flowing along these field lines from the magnetotail naturally funnel toward the polar regions where the field lines converge. As the electrons approach Earth, they encounter increasingly dense atmosphere. The atmosphere doesn't end abruptly. It gradually thins with altitude. At the altitude where the northern lights occur, roughly 100 to 300 kilometers above the surface, there's still enough air that incoming energetic electrons begin colliding with atmospheric atoms and molecules. These collisions are the key to creating visible light. When a fast-moving electron strikes an oxygen or nitrogen atom, it can transfer some of its energy to that atom, knocking one of the atom's electrons into a higher energy state. The atom is now in an excited state, holding more energy than is natural for it. Like a ball balanced on top of a hill, the excited atom is unstable and will return to its normal state by releasing that extra energy. In the case of atmospheric atoms, that energy is released as a photon, a particle of light. The color of the light depends on which type of atom was struck and how much energy it absorbed. Oxygen atoms, when excited by high-energy electrons, emit green light at a wavelength of 557.7 nanometers. This is the most common color seen in the aurora, the brilliant green that dominates most photographs of the northern lights. If the oxygen atoms are excited even more strongly, or if they're at higher altitudes where collisions are rarer and atoms have more time before emitting light, they produce red light at 630 nanometers. Nitrogen molecules, which make up most of Earth's atmosphere,
emit blue and purple light when excited. The exact mixture of colors in any auroral display depends on what altitude the electrons are penetrating to, how much energy they carry, and what atmospheric gases they encounter. But here's something that scientists only recently understood in detail. The auroral electrons don't deposit their energy randomly. They create distinct structures, curtains and arcs and rays that twist and fold in characteristic patterns. These structures are direct maps of what's happening in Earth's magnetic field high above. An auroral arc, for instance, marks the boundary between different regions of the magnetosphere with different plasma properties. When you see an auroral curtain waving like a flag in the wind, you're watching the effects of waves propagating through Earth's magnetic field. Oscillations that accelerate electrons in pulses. The rapid flickering sometimes seen in aurora, where the light seems to dance and shimmer on timescales of seconds, comes from very small-scale processes called alpha waves, a type of electromagnetic wave that can travel along magnetic field lines and accelerate electrons in tiny, concentrated bursts. For years, scientists debated exactly how these alpha waves accelerated electrons efficiently enough to create the brightest auroral displays. The problem was that simple theories of wave-particle interaction suggested the process shouldn't be powerful enough. The waves should dissipate before transferring enough energy to electrons. Something was missing from the models. The breakthrough came from a combination of satellite observations and laboratory experiments. Researchers discovered that under certain conditions in the magnetosphere, alpha waves don't remain smooth and uniform. They develop sharp gradients and parallel electric fields, concentrated regions where the electric field points along the magnetic field direction rather than perpendicular to it. In these regions, electrons can be accelerated extremely efficiently, gaining large amounts of energy in the span of just a few wave cycles. It's like the difference between a gentle ocean swell and a breaking wave. The gentle swell can rock a boat, but won't propel it strongly in any direction. A breaking wave, with its sharp face and concentrated energy, can catch that boat and send it surging forward. The parallel electric fields in alpha waves are like breaking waves for electrons, catching them and hurling them earthward with energies sufficient to penetrate deep into the atmosphere and create brilliant auroral light.
This mechanism had been theorized for years, but proving it required catching these waves in action with satellites positioned at just the right locations. In 2021, a team of researchers analyzing data from NASA's Time History of Events and Macro-Scale Interactions During Substorms mission, called TEMA, found definitive evidence of these parallel electric fields accelerating electrons in the magnetosphere during an auroral event. They were able to correlate satellite measurements of the waves with ground-based observations of aurora directly below, showing that when and where the parallel electric fields appeared, bright auroral arcs intensified on the ground. For the first time, scientists could draw a direct line from a specific mechanism in space to the light visible in the sky. This discovery filled in one of the last major gaps in understanding how the northern lights are created. But it also revealed something more profound about the nature of the aurora. The northern lights are not just a pretty side effect of space weather. They're a critical part of how Earth's magnetosphere releases energy. When the solar wind transfers energy into Earth's magnetic field through reconnection and other processes, that energy must eventually be dissipated, where the magnetosphere would continue building up energy indefinitely until something catastrophic occurred. The aurora is one of the primary mechanisms for energy dissipation. Those electrons slamming into the atmosphere and creating light are carrying energy from the magnetosphere and depositing it in the upper atmosphere as heat and light and chemical changes. The atmosphere absorbs this energy, warming slightly, and eventually radiates it away into space as infrared radiation. In essence, the northern lights are Earth's way of bleeding off excess energy transferred from the sun, a safety valve that prevents our magnetic field from overloading. Every photon of green or red or purple light you see in an auroral display represents energy that was once stored in magnetic fields stretched across millions of kilometers of space. Energy that has been converted and transformed through multiple steps, finally ending as visible light that impresses itself on your retina for a fraction of a second before vanishing forever. Understanding this process has taken humanity from the realm of myth into the realm of physics, from supernatural explanations to natural ones. But the journey isn't complete. Scientists are still discovering new aspects of how the aurora works, still finding surprises in data from satellites and ground-based observatories. One of the most recent surprises involves something called the electron diffuse aurora, a type of auroral light that doesn't form discrete arcs or curtains, but instead creates a faint, widespread glow across large regions of the sky. For decades, scientists thought they understood the diffuse aurora reasonably well. It was believed to be caused by electrons scattering off electromagnetic waves in a process that gradually randomized their motion, causing them to precipitate into the atmosphere over a wide area rather than in concentrated beams that create bright arcs. This explanation seemed to work and matched observations adequately. But in recent years, more detailed satellite measurements revealed that the diffuse aurora was far brighter than the scattering process could explain. The intensity of the glow suggested many more electrons were precipitating than theory predicted. Something else had to accelerate and direct electrons toward the atmosphere, something that operated over vast regions of space and affected millions of cubic kilometers of plasma simultaneously. The answer, when it emerged, was both elegant and complex. Researchers discovered that the magnetosphere is filled with different populations of waves, each with characteristic frequencies and wavelengths. These waves don't exist in isolation. They interact with each other and with particles in complicated ways. One type of wave, called Whistler mode chorus waves, turned out to be far more important than anyone had realized. These waves get their name from the sound they make when converted to audio frequencies. They sound like rising whistles or chirps, caused by a property where higher frequencies travel slightly slower than lower frequencies, creating a sweeping tone. Whistler mode chorus waves are generated by electrons themselves in a type of feedback loop. When certain conditions exist in the magnetosphere, particularly after energy injections from the magnetotail, electrons with specific energies and pitch angles become unstable and generate these waves. The waves then interact back with electrons, accelerating some and scattering others. It's a process of self-organization, where the plasma and electromagnetic fields constantly adjust to each other, creating patterns and structures that emerge from the complex interactions. What scientists discovered is that Whistler mode chorus waves are incredibly efficient at accelerating electrons to the energies needed to create diffuse aurora. A population of lower energy electrons drifting around Earth in the magnetosphere encounters these waves, and a subset of them get caught in a resonant interaction. Resonance occurs when the frequency of the wave matches the natural gyration frequency of the electron as it spirals around magnetic field lines. When this happens, energy transfers efficiently from the wave to the electron, and the electron gains speed. These newly energized electrons then precipitate into the atmosphere, creating the widespread glow of the diffuse aurora. This discovery explained the brightness mystery, but it also revealed that the magnetosphere is even more dynamic and interconnected than previously thought.
The same waves that create the diffuse aurora also play a role in forming Earth's radiation belts, the Van Allen belts, donut-shaped regions of space filled with trapped energetic particles that can damage satellites and pose a hazard to astronauts. The aurora, the radiation belts, and the overall behavior of Earth's space environment are all parts of the same interconnected system, all responding to the input of energy from the sun and all influencing each other through electromagnetic forces and particle interactions. This systems-level understanding represents a revolution in how scientists think about space weather and Earth's relationship with the sun. It's no longer sufficient to study the aurora in isolation or to treat Earth's magnetic field as a static background. Everything is connected. Everything influences everything else, and the northern lights are a window into this vast, interconnected system. When you watch aurora dancing overhead, you're seeing the visible manifestation of processes that extend from the sun's surface to Earth's upper atmosphere, processes that involve magnetic reconnection, particle acceleration, wave generation, and wave-particle interactions, spanning millions of kilometers and multiple domains of physics. The forgotten truth that scientists have revealed about the origin of the northern lights is that they're far more complex, far more dynamic, and far more interconnected with the larger space environment than anyone imagined even 20 years ago. But there's more to this story, another layer that takes us back in time to understand how Earth's magnetic field has changed over the history of our planet, and how those changes have affected the aurora over billions of years. The clues to this ancient history are written in rocks and minerals, locked into crystals that formed in Earth's distant past and preserved magnetic information like tiny time capsules. Reading these records has revealed something startling about Earth's magnetic field and, by extension, about the northern lights that field makes possible. Earth's magnetic field is not constant. It wanders, strengthens, weakens, and occasionally undergoes a complete reversal where north becomes south and south becomes north. Scientists have known about magnetic reversals since the 1960s, when they discovered patterns of magnetized rock on the ocean floor that recorded Earth's polarity flipping back and forth over millions of years. As new oceanic crust forms at mid-ocean ridges where tectonic plates pull apart, molten rock wells up from below and solidifies. As it cools, magnetic minerals in the rock align themselves with Earth's magnetic field at that moment, like tiny compass needles freezing in place. By mapping the magnetic orientations of rocks at different distances from the mid-ocean ridges, geologists created a timeline of magnetic reversals stretching back hundreds of millions of years. On average, Earth's magnetic field reverses every few 100,000 years, though the timing is highly irregular. The last reversal occurred about 780,000 years ago, meaning we're currently in an unusually long stable period. During a reversal, which can take anywhere from a few thousand to tens of thousands of years to complete, the magnetic field weakens dramatically, sometimes dropping to just 10% of its normal strength. During these periods of weak field, the magnetosphere shrinks and becomes less effective at shielding Earth from the solar wind. More solar particles reach the atmosphere, and aurora likely appear at much lower latitudes than normal, visible from tropical regions and possibly even globally. The effects on life during these reversals are debated. The increased radiation reaching the surface could certainly pose challenges for organisms, potentially causing increased mutation rates and affecting species that navigate using magnetic fields. But life has persisted through hundreds of reversals, suggesting that while challenging, these events are not extinction-level catastrophes. The aurora during these periods would have been spectacular and strange, dancing across skies where it had never been seen before. Visible to early humans and their ancestors,
possibly influencing migrations and behaviors in ways we can only speculate about. But the magnetic field's history goes back much further than the reversal record. Evidence from ancient rocks suggests that Earth has maintained a magnetic field for at least 3.5 billion years, possibly as long as 4.2 billion years, almost as old as the planet. This longevity is remarkable because generating a magnetic field through the dynamo process requires specific conditions: a liquid, electrically conductive outer core, and sufficient heat flow to drive convection. The fact that Earth has maintained these conditions for billions of years, while similar planets like Mars and Venus either never developed or lost their magnetic fields, speaks to something special about our planet's internal structure and evolution. The strength of Earth's magnetic field has varied considerably over geological time. Evidence from ancient rocks suggests that the field was stronger in the distant past, possibly because Earth's core was hotter and convection more vigorous. As the planet has cooled over billions of years, the magnetic field has gradually weakened, though this trend is superimposed on shorter-term fluctuations and reversals. About 41,000 years ago, something particularly interesting happened. Earth's magnetic field didn't reverse completely, but it weakened dramatically, and the magnetic poles shifted significantly from their normal positions in an event called the Lechamp excursion. For perhaps a few centuries, the field strength dropped to less than 1/4 of its current value. The aurora would have been visible much farther from the poles than usual, appearing regularly at mid-latitudes. This event occurred during an interesting period in human history. Anatomically modern humans had spread across much of Africa, Europe, and Asia. Neanderthals were nearing extinction in their last refuges in southern Europe.
The climate was in a glacial period, with ice sheets covering much of northern Europe and North America. Some researchers have speculated that the Lechamp excursion could have had effects on climate, on the extinction of Neanderthals, and on human cultural developments during this period. The increased cosmic ray flux reaching Earth's atmosphere during the weak magnetic field period would have increased the production of certain isotopes and could potentially have affected atmospheric chemistry and cloud formation. The evidence for dramatic effects remains controversial, but what's certain is that the night sky during this period would have looked fundamentally different, with aurora visible from places like the Mediterranean, North Africa, and the Middle East, regions where such sights would have been unprecedented in human experience. Ancient humans might have watched these lights and woven them into their mythologies in ways that have not survived in any records we can access today. The Lechamp excursion also left traces in another record, tree rings. The increased cosmic ray flux during the weak magnetic field period created more carbon-14 in the atmosphere. Trees growing during this time incorporated this carbon into their wood, and by measuring carbon-14 concentrations in ancient tree rings, scientists can identify the timing of the excursion with remarkable precision. This technique has allowed researchers to correlate the magnetic event with climate records, archaeological evidence, and other geological phenomena, building a detailed picture of Earth during this unusual period. Studying ancient magnetic fields through rocks and minerals is called paleomagnetism, and it has revealed not just the history of Earth's magnetic field, but also information about tectonic plate movements, ancient climates, and even the formation of mineral deposits. Certain types of magnetic minerals form only under specific conditions of temperature and oxygen availability, and their presence in rocks provides clues about the environment when those rocks formed. Iron oxide minerals, called magnetite and hematite, are particularly important for paleomagnetic studies. These minerals are strongly magnetic and resistant to alteration over geological time, preserving their magnetic alignment for billions of years under the right conditions. By carefully extracting samples from ancient rock layers and measuring the magnetic orientation of minerals within those samples, scientists can reconstruct the direction and intensity of Earth's magnetic field when the rocks formed. This work has revealed another fascinating aspect of Earth's magnetic field. It moves. The magnetic North Pole, The point where field lines point straight down into Earth is not fixed at the geographic North Pole. Currently, the magnetic North Pole is located in the Arctic Ocean, north of Canada, but it's moving rapidly northward toward Russia at about 50 kilometers per year. This movement has accelerated in recent decades, possibly indicating that something significant is changing in the dynamics of Earth's core. Navigators and map makers must regularly update their charts to account for this wandering. The direction a compass points, called magnetic declination, varies depending on where you are on Earth and slowly changes over time as the magnetic field shifts. In some locations, the declination is minimal, and magnetic north is close to true north. In other places, the difference can be 20 degrees or more. Hikers, sailors, and pilots must account for this difference when navigating by compass, and the values they use today would be wrong if used a century from now as the field continues its restless movement. This movement of the magnetic poles means that the auroral ovals, the regions where aurora most commonly appear, also move. They're not centered on the geographic poles, but on the magnetic poles, and as those poles shift, so too do the best locations for viewing northern lights. Places that saw frequent aurora centuries ago might rarely see them today, while new locations have gained prominence as aurora viewing destinations. This slow dance of the magnetic field connects the aurora of the present with the aurora of the past and future. A reminder that the light show we see today is just one frame in a billion-years-long film of Earth's magnetic activity. The connection between Earth and Sun, mediated by the magnetic field and made visible through aurora, is not unique to our planet. Similar phenomena occur throughout the solar system, wherever planets or moons have magnetic fields and atmospheres. Jupiter, the giant of our solar system, has the most powerful magnetic field of any planet, thousands of times stronger than Earth's. Its aurora are correspondingly spectacular, though visible primarily in ultraviolet wavelengths rather than visible light. Jupiter's aurora are powered not just by the solar wind, but also by the planet's rapid rotation and by volcanic activity on its moon, Io, which spews charged particles into space that get swept up by Jupiter's magnetic field. Saturn also has aurora, as do Uranus and Neptune, though they've been studied far less due to the difficulty of sending spacecraft to those distant worlds. Even planets without global magnetic fields can have aurora of a sort. Mars has localized crustal magnetic fields in certain regions, remnants of a global magnetic field that died billions of years ago when the planet's core cooled and its dynamo shut down. In these regions, the solar wind can interact with the local magnetic fields to create faint aurora, discovered by spacecraft orbiting Mars. Venus, which has no magnetic field at all, experiences aurora on its night side, where the solar wind interacts directly with the upper atmosphere, creating a completely different type of auroral process than occurs at Earth. Even moons can have aurora.
Ganymede, one of Jupiter's large moons, is the only moon in the solar system with its own magnetic field, and it has aurora similar in some ways to Earth's, though modified by its location within Jupiter's giant magnetosphere. These solar system aurora tell scientists that the physics underlying the northern lights is universal, occurring wherever certain conditions exist: a source of energetic particles, a magnetic field to guide them, and an atmosphere for them to collide with. By studying aurora on other worlds, scientists gain perspective on Earth's aurora and learn about the range of possible behaviors these phenomena can exhibit. The study of aurora has practical implications beyond scientific curiosity. Understanding how aurora are generated helps us understand space weather more broadly, and space weather affects technology that modern civilization depends on. The same energetic particles that create beautiful lights in the sky can also damage satellites, disrupt radio communications, interfere with GPS signals, and induce currents in power grids that can cause blackouts. During major geomagnetic storms, airlines must reroute flights that would normally travel over polar regions because increased radiation at high latitudes can expose passengers and crew to elevated doses and can disrupt communication between aircraft and ground control. Astronauts on the International Space Station must sometimes take shelter in more heavily shielded parts of the station when a major solar particle event occurs. Satellite operators must carefully manage their spacecraft during storms to prevent damage to sensitive electronics. Power grid operators monitor space weather forecasts and take precautions to prevent the kind of transformer damage that occurred during a major geomagnetic storm in 1989, which knocked out power to most of Quebec for 9 hours. The economic impact of space weather is substantial. Estimates suggest that a severe geomagnetic storm comparable to the Carrington event of 1859, if it occurred today, could cause trillions of dollars in damage to global infrastructure and take years to fully recover from. The interconnected nature of modern electrical systems means that failures could cascade, with damaged transformers in one region affecting the stability of the grid across entire continents. Communications systems, from cell phones to internet infrastructure, rely on satellites that are vulnerable to space weather. GPS, which modern agriculture, transportation, and finance all depend on, can become unreliable or unusable during major geomagnetic disturbances. For these reasons, governments and international organizations have invested heavily in space weather forecasting and preparedness. Networks of satellites monitor the sun continuously, watching for flares and coronal mass ejections that could threaten Earth. When a potentially dangerous eruption is detected, warnings are issued to power companies, satellite operators, airlines, and other affected industries. Ground-based magnetometers around the world measure Earth's magnetic field continuously, providing real-time information about geomagnetic activity. All sky cameras in auroral regions photograph the sky every few seconds, and the patterns they capture are used to infer what's happening in the magnetosphere high above. Scientists have developed complex computer models that simulate the behavior of the magnetosphere, taking solar wind conditions as inputs and predicting where and when aurora will appear, how strong geomagnetic disturbances will be, and what effects might be expected on various technologies. These models have improved dramatically in recent years as understanding of the underlying physics has deepened and as computing power has grown, but they're still imperfect. The magnetosphere is a complex, non-linear system where small changes in conditions can sometimes lead to vastly different outcomes, making precise predictions difficult. Despite these challenges, space weather forecasting has reached a level of maturity where it provides genuine value for protecting infrastructure and human activities. The work continues to improve as new satellite missions are launched and as theoretical understanding advances. Each new discovery about how aurora are generated, about how magnetic reconnection operates, about how waves and particles interact in the magnetosphere, feeds into better models and better forecasts. The Northern Lights, once purely a source of wonder and myth, have become a practical concern for a technological civilization that extends its reach into space and that depends on systems vulnerable to the space environment. Yet for all the practical concerns and scientific understanding, the aurora retain their power to inspire awe. People still travel to the Arctic in winter, enduring cold and darkness for a chance to see the lights dance overhead. Photographers spend hours in freezing temperatures, capturing images of green curtains and purple arcs against star-filled skies. The aurora appear in art and literature, in music and film, as a symbol of nature's beauty and mystery.
There is something profound about standing beneath the northern lights, watching them shift and shimmer in silence, feeling the cold air on your face while light from space paints the sky. It connects us to something larger than ourselves, to the sun and the solar wind, to Earth's magnetic field generated in molten iron thousands of kilometers beneath our feet, to processes that have been occurring for billions of years and will continue long after humanity has gone. The aurora remind us that Earth is not a closed system, isolated from the cosmos. We live on a planet bathed in radiation and particles from our star, protected by invisible fields and forces we cannot directly perceive, but which are absolutely essential for our existence. Every breath we take is possible because the magnetosphere and atmosphere work together to shield us from the harshest effects of the space environment.
Every auroral photon is evidence of this protection in action. Energy being safely dissipated as light rather than reaching the surface to damage living tissue. Understanding this makes the northern lights more meaningful, not less. Knowing the physics behind the phenomenon doesn't diminish the experience of watching them. If anything, it deepens the wonder. You're not just seeing pretty colors in the sky, you're witnessing the interaction of two vast systems, watching in real time as energy flows from sun to earth and is converted through multiple steps into something your eyes can detect. You're seeing magnetism made visible, plasma physics on a planetary scale, the results of events that began 93 million miles away and ended in the atmosphere 100 kilometers above your head. The northern lights are a bridge between the everyday world we inhabit and the universe beyond, between human experience and cosmic processes. They've been appearing in Earth's skies for as long as the planet has had an atmosphere and magnetic field, viewed by countless generations of humans and pre-humans, by dinosaurs and trilobites and single-celled organisms drifting in ancient seas. They'll continue appearing long after our civilization has vanished, long after our species has either evolved into something new or gone extinct. The physics of the aurora is indifferent to human observers, yet humans have always been drawn to these lights, always sought to understand them, to explain them, to incorporate them into our understanding of the world. In that sense, the scientific understanding of aurora is part of a tradition that stretches back to the first humans who wondered what those lights were, who told stories to make sense of them, who passed those stories down through generations. We're still telling stories about the northern lights, but now our stories are written in the language of mathematics and physics, tested against observation and refined through experiment. The story we tell today about the origin of the aurora is almost certainly not the final story. Future discoveries will add new chapters, will revise our understanding in ways we can't yet predict. But the story we have now is remarkable in its scope and detail, connecting phenomena from the quantum scale of particle interactions to the planetary scale of Earth's magnetic field, from time scales of microseconds for wave-particle interactions to billions of years of planetary evolution. This is the forgotten truth that scientists have revealed, or perhaps not forgotten, but newly discovered. The northern lights are not a simple phenomenon with a single cause. They're the visible tip of an enormous, complex system that spans the distance from sun to earth and involves some of the most fundamental processes in plasma physics. They're a safety valve for Earth's magnetosphere, a diagnostic of space weather, a hazard for technology, a subject of myth and art, and a window into how our planet interacts with the star that gives us life. As you drift towards sleep, imagine yourself floating high above the Arctic, looking down at the aurora from above, as astronauts sometimes do from the International Space Station. From that vantage, you can see the entire auroral oval, a ring of light circling the magnetic pole. You watch as streamers and curtains form and dissolve, as the oval expands during a substorm, when energy stored in the magnetotail suddenly releases. You're witnessing the magnetosphere breathing, energy flowing in from the solar wind and flowing out through the aurora. Now imagine yourself rising even higher, out beyond Earth's atmosphere, into the magnetosphere itself. Around you, invisible to your eyes, but present nonetheless, are magnetic field lines arcing from pole to pole, spiraling and twisting under the influence of the solar wind. Particles trapped on these field lines spiral and bounce, forming the radiation belts. In the distant magnetotail, you sense rather than see the process of magnetic reconnection occurring, field lines breaking and reconnecting, converting magnetic energy into particle energy, launching plasma back toward Earth. Waves ripple through the plasma around you, Whistler mode chorus singing their rising tones, and Alphen waves stretching and compressing field lines. The entire magnetosphere is alive with motion and energy transfer, a vast electromagnetic ecosystem with Earth at its center. Further out still, you encounter the boundary of the magnetosphere, the magnetopause, where Earth's magnetic field meets the solar wind and holds it at bay. The boundary ripples and waves under the varying pressure of the wind. Occasionally, the wind pressure increases suddenly as a coronal mass ejection arrives and the magnetopause compresses inward, pushed closer to Earth. The magnetosphere responds, storing energy, eventually releasing it in a substorm that lights up the aurora below. You realize you're watching a battle that has been ongoing for billions of years, the solar wind trying to strip away Earth's atmosphere and magnetic field. Earth's magnetic field generated by its internal dynamo holding firm, deflecting the wind around the planet like water flowing around a boulder in a stream. And now travel outward one final time, away from Earth, past the moon's orbit, through the interplanetary medium with its tangled magnetic fields and particle streams. Approach the sun, our star, the source of all this activity. Descend toward its surface and witness the seething chaos, the granulation caused by convection cells as hot plasma rises and cooler plasma sinks, the dark sunspots where magnetic fields suppress convection, the sudden flares where magnetic energy releases explosively. Watch as a coronal mass ejection erupts, billions of tons of plasma hurled into space at millions of kilometers per hour, riding on magnetic field lines dragged from the sun's interior. This is where the story of the aurora begins, in the magnetic chaos of our star's atmosphere.
The ejected plasma will take days to reach Earth, will slam into the magnetosphere, will transfer energy that will eventually cascade through multiple steps and finally appear as light in the polar skies, completing a journey from nuclear fusion in the sun's core through interplanetary space to human retinas looking upward from the surface of a planet. This is the forgotten truth about the Northern Lights, the truth that scientists have painstakingly revealed over centuries of observation and decades of space exploration. These lights connect us to the sun, to the physics of plasmas and magnetic fields, to the history of our planet, and to the future of our technological civilization. They are both more complex and more comprehensible than our ancestors could have imagined, more beautiful for being understood rather than less. But there is another dimension to this story, one that connects the aurora to the deeper history of our solar system, and to the question of how common such phenomena might be in the universe. When Earth first formed 4.5 billion years ago, it was a very different world. The planet was molten, heated by the violence of its formation as countless asteroids and planetesimals collided and merged. The early atmosphere, if it can be called that, was probably blown away by the young sun's intense solar wind and by the impacts of massive objects. There is no ocean, no life, no magnetic field. But as the planet cooled and differentiated, with heavy metals sinking toward the center and lighter materials rising to form a primitive crust, conditions for a magnetic field began to develop. The core separated into a solid inner core of iron and nickel and a liquid outer core, where convection could occur. At some point, perhaps within the first few 100 million years of Earth's existence, the dynamo began operating and the planet gained its protective magnetic field. With that field came the first aurora, dancing above a landscape of barren rock and lava flows, with no eyes to witness them. The early solar wind was much more intense than today's. Young stars like the early sun are more active, prone to frequent flares and coronal mass ejections. The space environment in the young solar system would have been harsh, with radiation levels far higher than present day. Earth's newly formed magnetic field was crucial for protecting whatever atmosphere could accumulate through volcanic outgassing. Without that field, Earth might have suffered the fate of Mars, losing most of its atmosphere to the solar wind and becoming a cold, dry world unable to support life. The aurora on early Earth would have been frequent and intense, powered by the vigorous solar wind and by a magnetic field that may have been stronger or differently configured than today's. As the planet evolved and life emerged, the aurora continued their vigil overhead, unseen witnesses to the transformation of Earth from a lifeless rock to a world teeming with organisms. The first photosynthetic bacteria that began producing oxygen around 2.5 billion years ago did so under skies that regularly displayed aurora lights. The oxygen they produced gradually accumulated in the atmosphere, rusting iron on the surface and fundamentally changing the chemistry of the planet. This great oxidation event made Earth suitable for complex life, but it was made possible by the magnetic field that kept the atmosphere from being stripped away, and the aurora were the visible signature of that protection. Through billions of years of evolution, through mass extinctions and radiations of new life forms, through continental drift and climate changes, the aurora remained constant in their fundamental nature, even as their details varied with changes in the magnetic field and solar wind. When the first animals developed eyes sensitive to visible light, perhaps 600 million years ago, the aurora became visible to living things for the first time. What did a trilobite make of lights in the water above it, filtered through ocean waters but perhaps visible on clear nights in shallow seas? Of course, a trilobite had no capacity for wonder, no ability to question what it saw, but it registered photons from the aurora nonetheless, connecting life and space weather in the most direct way. The fish that evolved from those early animals, the amphibians that crawled onto land, the reptiles and dinosaurs and early mammals, all lived under skies where aurora appeared when geomagnetic conditions were right. The asteroid impact that ended the age of dinosaurs 66 million years ago would have been accompanied by spectacular auroral displays as the impact ejected material into space that then rained back down, heating the upper atmosphere and creating unusual ionization. The world burned and then froze in the aftermath, and through it all, the aurora continued, indifferent to the extinction event unfolding below. The mammals that inherited the post-impact world diversified and evolved, eventually giving rise to primates and then to the genus Homo. Early hominins in Africa millions of years ago lived too far from the poles to regularly see aurora, but as humans and their relatives spread into Eurasia and eventually into northern latitudes, they entered the auroral zone. Neanderthals living in Ice Age Europe would have seen the northern lights during their most active periods, particularly during the Le Champ excursion 41,000 years ago, when weak magnetic field strength brought aurora to Mediterranean latitudes. What stories did they tell about these lights? We'll never know, as Neanderthals left no written records and their oral traditions died with them, but they had the cognitive capacity for language and abstract thought, and it's hard to imagine they didn't try to explain the lights in some way. Anatomically modern humans certainly did. Every culture that encountered aurora developed explanations and incorporated them into mythology.
The Norse saw the Bifrost Bridge to Asgard, or the reflections from Valkyrie shields. The Sami people of northern Scandinavia treated the aurora with respect and caution, believing they were powerful spirits that could be dangerous if provoked. Children were warned not to whistle at the lights or wave white cloths, lest they attract the attention of the spirits and be carried away. Across the Arctic, numerous indigenous cultures developed similar traditions of treating aurora as spiritual entities, as ancestors, or as supernatural forces. In Finland, as mentioned earlier, the aurora were believed to be caused by a magical fox running across snow and sweeping its tail upward to create sparks. The Finnish word for aurora, revontulet, literally means foxfires. In some Chinese records dating back over 2,000 years, aurora visible at lower latitudes during strong geomagnetic storms were described as dragons fighting in the sky. In medieval Europe, aurora appearing at mid-latitudes were sometimes interpreted as portents of disaster, as battles of warriors in the sky, or as signs from God. The appearance of bright red aurora visible across Europe in 1583 was widely documented and interpreted through various cultural and religious lenses. These cultural responses to aurora tell us something important about human nature. We are pattern-seeking creatures who try to make sense of our environment. When confronted with something we don't understand, we create explanations that fit within our existing frameworks of knowledge and belief. For most of human history, those frameworks were mythological and religious. The aurora were too far beyond everyday experience to be explained through ordinary cause and effect, so they were placed in the realm of the supernatural. This is not a failing, but simply a reflection of the knowledge available at the time. The shift from supernatural to scientific explanations of aurora came gradually, beginning in the Age of Exploration, when European scientists began systematically studying the phenomenon. In the early 1600s, Galileo coined the term aurora borealis, combining the name of the Roman goddess of dawn with the Greek word for north wind. He had observed unusual lights in the sky and was trying to understand them, though his explanation that they were sunlight reflecting off atmospheric vapors was incorrect. Other scientists of the era proposed that aurora were caused by sunlight reflecting off polar ice or by light from below the horizon refracting through the atmosphere. All these early explanations were wrong, but they represented attempts to explain aurora through natural processes rather than supernatural ones, an important conceptual shift. The connection between aurora and magnetic activity began to be recognized in the 1700s. Scientists noticed that compasses behaved erratically during bright auroral displays, suggesting some link between the lights and Earth's magnetic field. In the 1800s, the connection between auroras and solar activity started to become apparent, particularly after the Carrington event demonstrated dramatically that events on the sun could affect Earth's magnetic field and create aurora. But the mechanism remained mysterious. How could something happening on the sun, millions of miles away, affect Earth so quickly and so strongly? The breakthrough came in the early 1900s with the development of the theory of the ionosphere, a layer of Earth's upper atmosphere where atoms are ionized by solar radiation. Scientists proposed that electrical currents flowing in the ionosphere could create the lights of the aurora, But this still didn't explain where the energy came from or how it reached Earth. The discovery of the solar wind in the late 1950s and early 1960s provided the missing piece. Particles streaming from the sun could carry energy to Earth's magnetosphere, and somehow that energy was being converted into the kinetic energy of electrons that then collided with atmospheric atoms to create light. Over the following decades, through a combination of theoretical work, laboratory experiments, and increasingly sophisticated satellite observations, the picture became clearer. Each piece of the puzzle, from magnetic reconnection to wave-particle interactions to the structure of Earth's magnetosphere, was painstakingly worked out through the efforts of thousands of scientists around the world. This process of discovery is itself a fascinating story, a testament to human curiosity and persistence. Many of the scientists who contributed to understanding the aurora never saw the lights themselves. They worked in laboratories and universities far from the auroral zones, analyzing data from satellites, running computer simulations, developing mathematical models. Some of the key discoveries came from unexpected places. The theory of magnetic reconnection, for instance, was initially developed in the 1950s by scientists studying plasma containment for fusion reactors. They were trying to understand why plasmas in magnetic containment systems were unstable and lost energy. The insights they gained turned out to apply perfectly to what was happening in Earth's magnetotail, even though that wasn't what they were investigating. This is how science often works, with ideas and techniques developed for one purpose, finding unexpected applications in seemingly unrelated fields. The study of the aurora has benefited from advances in many areas of physics and engineering. The development of spacecraft capable of surviving in the harsh space environment and making precise measurements of particles and fields was essential. Advances in computer technology made it possible to run simulations of the magnetosphere that would have been inconceivable even a few decades ago. New techniques in ground-based observation, from all-sky cameras to radar systems that can measure electron densities in the ionosphere, provided complementary data to spacecraft observations. Each technological advance opened new windows on the aurora and revealed previously hidden aspects of the phenomenon. Today, the study of aurora is a mature field, with a strong theoretical foundation and a wealth of observational data, but it's far from complete. New discoveries continue to surprise researchers and refine understanding.
The recent findings about parallel electric fields in Alphen waves, about the importance of Whistler mode chorus waves, about the complex interplay between different acceleration mechanisms, all came within just the past few years. Future satellite missions will provide even more detailed observations, measuring the magnetosphere with finer spatial and temporal resolution. New modeling techniques, particularly those using artificial intelligence to find patterns in the vast amounts of data being collected, promise to reveal relationships and processes that aren't obvious to human observers. The story of the aurora is still being written. And this brings us to a profound question. Are we alone in the universe in experiencing this phenomenon? Aurora require three ingredients: an atmosphere, a magnetic field, and a source of energetic particles. We know these ingredients exist elsewhere in our solar system, and we've detected aurora on several other planets. But what about planets orbiting other stars? Exoplanets, of which we've now discovered thousands. Could there be aurora on worlds circling distant suns? And if so, what might they tell us about those alien worlds? The search for exoplanet aurora is in its infancy, but it's an active area of research. Astronomers have detected radio emissions from some exoplanets
that could be signatures of auroral activity. On Earth, aurora emit not just visible light, but also radio waves at certain frequencies, produced by the same energetic electrons that create the visual display. These radio emissions can be detected at much greater distances than visible light, making them potentially observable from other star systems. Several exoplanets, particularly hot Jupiters, gas giant planets orbiting very close to their stars, have been proposed as candidates for detectable auroral radio emission. These planets exist in intense radiation environments, bombarded by stellar winds much more powerful than our solar wind. If they have magnetic fields, and many probably do, then they should have aurora far more intense than anything in our solar system. The challenge is detecting the radio emissions from these distant auroras against the background noise of the cosmos and the radio emissions from the stars themselves. As radio telescope technology improves and new facilities come online, this should become increasingly feasible. The detection of aurora on an exoplanet would be scientifically valuable for several reasons. It would confirm the presence of a magnetic field, which tells us about the planet's interior structure and thermal evolution. It would provide information about the stellar wind environment, helping us understand the space weather around other stars. And for planets that might be potentially habitable, the presence of a strong magnetic field creating aurora would be encouraging, suggesting the planet has protection from stellar radiation similar to what Earth's magnetic field provides. In the search for life elsewhere in the universe, magnetic fields and aurora might be important factors to consider, markers of worlds where surface conditions could be stable and protected over long timescales. There's something poetic about the idea that aurora might be a universal phenomenon, occurring throughout the galaxy wherever the right conditions exist. That on a planet orbiting a star in the Andromeda galaxy, lights might be dancing in alien skies above an alien landscape, governed by the same physics that creates Earth's northern lights. The equations of electromagnetism and plasma physics are the same everywhere in the universe. The fundamental forces and particles that produce aurora here would produce them there as well. We are connected to the cosmos not just through the atoms in our bodies, forged in ancient stars, but through the physics that governs natural phenomena from the smallest scales to the largest. The aurora are a reminder of this deep connectedness, this unity of physical law that makes the universe comprehensible. As your mind relaxes further, as sleep draws closer, consider this. You exist on a planet that has been protected by a magnetic field for billions of years, a field that makes visible its protective work through the beauty of aurora. Your ancestors, back through countless generations, lived under the same protection, witnessed the same lights, wondered about their meaning. The atoms in your body were forged in stars that died before our solar system formed, scattered through space, eventually incorporating into the disk of gas and dust that collapsed to form the sun and planets. Some of those atoms passed through the solar wind, that invisible stream of particles flowing from the sun. Some were struck by cosmic rays, high-energy particles from distant supernovae and other energetic events in the galaxy. You are made of stardust, shaped by evolution, protected by magnetism, witness to lights that connect Earth to sun and present to past. In understanding the northern lights, we understand something essential about our home in the cosmos, about the delicate balance of forces that makes our world habitable, about the ongoing conversation between Earth and Sun, conducted in the language of particles and fields, and electromagnetic radiation. But the story doesn't end there, because understanding something scientifically doesn't mean we've exhausted its meaning or significance. The aurora exists at an intersection between science and human experience, between objective physical processes and subjective aesthetic response. A physicist measuring electron precipitation rates with satellite instruments, and an artist photographing green curtains rippling across the night sky are both engaging with the same phenomenon, but in fundamentally different ways. Neither approach is complete without the other. The data tells us what is happening, but the experience tells us what it means to be human in the presence of something larger than ourselves. Throughout history, the aurora have inspired not just scientific inquiry, but artistic creation. Poets have written about the lights, musicians have composed pieces evoking their movement and mystery, painters have attempted to capture their colors and forms on canvas. In the age of photography, the aurora have become one of the most photographed natural phenomena, with countless images shared online showing the lights in various forms and colors, often reflected in lakes or silhouetted against mountains. These images circulate globally, bringing the experience of aurora to people who may never visit the Arctic themselves, spreading the wonder and beauty beyond the narrow latitudes where the lights are visible. The rise of aurora tourism has created a new economic relationship with the phenomenon. Communities in northern Norway, Iceland, Alaska, and Canada have built industries around bringing visitors to see the northern lights. Hotels advertise their aurora viewing opportunities. Tour operators offer aurora chases, where they drive groups to locations with clear skies, and entire festivals celebrate the lights. This commercialization might seem to diminish the aurora, to reduce them to a commodity, but it also creates a constituency of people who have personal experiences with the lights and who develop a sense of connection to the Arctic regions where they're visible. Some indigenous communities have mixed feelings about aurora tourism. On the one hand, it brings economic opportunities to remote regions that often have limited economic bases. On the other hand, it can feel like an appropriation of something that has deep cultural significance, turning a spiritual phenomenon into entertainment for outsiders. There are also practical concerns about the environmental impact of increased tourism, the light pollution from tourist facilities that makes aurora viewing worse, and the cultural insensitivity of visitors who don't understand or respect local traditions regarding the lights. These tensions reflect broader issues about how we relate to nature and natural phenomena in the modern world, about who has the right to experience and interpret things, about the balance between economic development and cultural and environmental preservation. The aurora belong to everyone and to no one, visible from international waters and from multiple countries, the product of processes that operate on planetary and solar scales beyond any human jurisdiction. Yet they're also deeply meaningful to specific communities who have lived with them for generations, who have developed relationships with the lights that go beyond visual appreciation to encompass spiritual and cultural dimensions. Respecting both the universal and the particular aspects of aurora, the scientific and the cultural, the aesthetic and the spiritual, requires a kind of conceptual flexibility that isn't always easy to maintain. It's tempting to privilege one type of understanding over others, to say that the scientific explanation is the true one and everything else is merely subjective interpretation, or conversely, to say that scientific understanding is cold and reductive and misses what's really important about the aurora. But this is a false dichotomy. The universe is large enough to accommodate multiple valid perspectives on the same phenomenon. The aurora are simultaneously energetic electrons colliding with atmospheric atoms, and spirits dancing in the sky, and photographic subjects, and tourist attractions, and subjects of scientific study, and sources of geomagnetic disturbances affecting technology. All these descriptions are true at the same time, each capturing a different facet of a complex reality. This multiplicity of meanings is itself significant. It reflects the richness of human culture and consciousness, our ability to relate to the world through multiple modes of understanding simultaneously. A person watching the aurora can know the physics behind them while also experiencing wonder and aesthetic pleasure, can appreciate them as scientific phenomena and as sources of beauty, can understand them as natural processes and as cultural symbols. The human mind is capable of holding multiple frameworks simultaneously, of seeing the world through scientific and artistic and spiritual lenses at once without contradiction. Perhaps this is the deepest truth that the Northern Lights reveal, that the universe is both comprehensible and mysterious, that understanding something doesn't diminish it but enriches it, that knowledge and wonder are not opposed but complementary. The more we learn about the aurora, the more remarkable they become. The chain of causation from nuclear fusion in the sun's core to photons striking a retina on Earth spans incredible distances and timescales, involves phenomena at every scale, from quantum to planetary, and yet it's all connected, all part of a comprehensible system governed by physical laws we can discover and understand. That we, as conscious beings made of matter, can understand the processes that govern matter and energy in the universe is itself astonishing. We are the universe becoming aware of itself, asking questions about its own nature and finding answers. The aurora are both the question and part of the answer, both the mystery that prompted inquiry and the phenomenon that helps us understand the larger system in which we're embedded. They stand at a threshold between the known and unknown, the visible and invisible, the terrestrial and the cosmic. In many ways, the study of aurora represents science at its best, driven by curiosity about something beautiful and mysterious, pursued through observation and theory and experiment, collaborative across nations and disciplines, practical in its applications to protecting technology and forecasting space weather, yet also fundamental in advancing our understanding of plasma physics and planetary magnetospheres. The scientists who study aurora are explorers, mapping unknown territory, detectives solving puzzles, storytellers crafting narratives about how nature works. Their work continues the long human tradition of trying to understand our place in the cosmos, using modern tools and techniques, but driven by the same impulse that led ancient peoples to explain the lights through mythology. We've come a long way from the stories of foxfires and warrior shields, but we're still telling stories about the aurora, still using them to understand our relationship with the sun and earth and sky. The stories have changed as our knowledge has increased, but the fundamental human response to the lights, that mixture of wonder and curiosity and desire to understand, remains constant across cultures and centuries. If you could somehow gather everyone who has ever seen the Northern Lights, from a Neanderthal in Ice Age Europe to a modern tourist in Iceland, from an Inuit hunter to an astronaut on the space station, from a medieval peasant to a plasma physicist, and ask them what they saw, you would get vastly different answers, shaped by culture and knowledge and individual perspective. Yet there would also be commonalities, that sense of witnessing something extraordinary, something that transcends everyday experience and points toward larger realities beyond immediate perception. The aurora have this power because they are genuinely extraordinary, rare enough that many people never see them, spectacular enough that those who do never forget the experience, and mysterious enough that they invite interpretation and meaning-making. They occupy a perfect niche in human consciousness, tangible and observable, but not mundane, scientifically explicable, but not fully predictable, beautiful, but also slightly uncanny, especially when they move rapidly or appear in unusual colors. There's a reason the aurora appears so frequently in art and literature as symbols and metaphors, as representations of the sublime or the transcendent or the alien. They fit our aesthetic and psychological needs for encounters with something beyond the ordinary. As you drift closer to sleep, your breathing slow and regular, your body heavy and relaxed, imagine the aurora one more time, not from the ground looking up, or from space looking down, but from within the phenomenon itself. You're suspended in the upper atmosphere, 100 kilometers above Earth's surface, where the air is so thin it's almost vacuum. Around you, oxygen atoms and nitrogen molecules drift in the near emptiness, their paths determined by thermal motion and Earth's gravity. Below you, the curve of the planet stretches away in all directions, a vast sphere of rock and water, wrapped in a thin film of air. Above you, the stars shine with unwavering brilliance in the black sky, undimmed by atmospheric scattering. And now the electrons arrive, accelerated from the magnetosphere, spiraling down magnetic field lines, carrying energies of thousands of electron volts. They slam into atoms near you, transferring their energy in collisions that happen too fast for perception, on timescales measured in femtoseconds. The atoms, kicked into excited states, relax back to their ground states, emitting photons as they do so. Green light from oxygen, blue and purple from nitrogen, sometimes red from high-altitude oxygen transitions. The photons stream downward and upward, some eventually reaching eyes on the ground where they trigger chemical reactions in retinal cells that send electrical signals to brains that interpret them as light and color and beauty. You're part of the process now, suspended between Earth and space, between matter and energy, between particle and wave. The aurora flow around and through you, a river of light made from the raw materials of the universe, powered by the sun, guided by magnetism, made visible by the quantum mechanical properties of atoms. Time seems to slow, or perhaps to lose meaning altogether. The distinction between the past and present blurs.
This moment of auroral activity could be happening now, in the year 2025, or 4 billion years ago, on a young Earth just developing its magnetic field, or 4 billion years in the future, on an Earth grown strange through geological change and biological evolution. The physics is the same across all those times. Electrons collide with atoms, energy converts to light, the aurora dance in the sky. The specifics vary: the strength of the magnetic field, the composition of the atmosphere, the intensity of the solar wind, but the fundamental process continues, has continued, will continue, as long as Earth retains its magnetic field and atmosphere. You realize you're witnessing something both ephemeral and eternal, a specific auroral display that will never be exactly repeated, but also an instance of a process that has repeated countless times and will repeat countless more. Each auroral photon exists for only a fraction of a second, traveling from its source to its destination and then vanishing, absorbed by whatever it strikes. But the aurora as a phenomenon persists, renewed moment by the constant flow of energy from sun to earth. It's like a waterfall, where the water you see is never the same water from moment to moment.
Yet the waterfall itself is a stable, persistent structure. The aurora are a waterfall of light, fed by the solar wind, channeled by the magnetic field, made visible in the atmosphere. Let yourself become that light, streaming from atom to eye, carrying information about the space environment, about the sun's activity, about Earth's magnetic field. You are energy in transit, neither particle nor wave, but something that can manifest as either, depending on how you're observed, quantum mechanical and classical at once, part of a system that extends from the nuclear reactions in the sun's core to the neurological responses in a human brain processing visual input. Everything is connected. Everything flows into everything else. Energy and matter and information transforming and transferring through every possible path. The boundary between you and the universe dissolves. You are the aurora, and the aurora are you. Patterns of energy moving through space and time, temporarily cohering into forms that seem distinct but are actually part of the larger flow. Your body, lying in bed, breathing slowly, is a configuration of atoms that will eventually disperse and reconfigure into other forms. The energy that powers your thoughts and heartbeat came from food that came from photosynthesis, that came from sunlight, that came from fusion in the sun. You are solar powered, part of the same system that creates the aurora, part of the dance of energy that encompasses the entire solar system and beyond. In this state, understanding and experience merge. Knowledge about the aurora doesn't stand separate from the feeling of watching them, but becomes part of a unified apprehension of the phenomenon in all its dimensions. Scientific understanding enriches aesthetic experience, and aesthetic experience motivates scientific inquiry. The cycle is complete, self-reinforcing, a positive feedback loop that drives both art and science forward. This is perhaps the final forgotten truth about the Northern Lights. They are teachers, showing us how to integrate different ways of knowing, demonstrating that the universe is both explicable and wondrous, that we can be both observers and participants, both separate from nature and part of it. But even this truth is not truly forgotten, just sometimes overlooked or underemphasized in discussions that focus on one aspect or another. The aurora have always had this teaching role, from ancient mythologies that use them to explain human relationships with the cosmos, to modern physics that uses them to understand plasma behavior. They meet us wherever we are and offer lessons appropriate to our level of understanding. To a child, they might teach simply that the world is full of surprising and beautiful things. To a scientist, they might teach about magnetospheric dynamics.